We are now beginning Chapter 9, where we will be looking at exponential and logarithmic functions. What we're going to be primarily concerned with, especially in the first section, is functions that involve variables that show up in the exponent. While we've seen exponents throughout the term, we have not considered cases where variables might be in the exponent, especially if that's the variable that we want to solve for in an equation. So a function like 2 to the x instead of x squared is an exponential function. And now, in order to solve exponential functions, we will need to introduce first the concept of inverse functions, and then what is the inverse function of the exponential, namely the logarithmic function. That's going to be the function that cancels out the exponential, that allows us to get the variable out of the exponent. So let's begin by looking at what's going to be actually fairly simple to deal with, but the first time we've introduced it, the concept of exponential functions, section 9.1. In section 9.1, we start with a definition. We're going to consider that for any real number, where that real number is positive and not equal to 1, that f of x equals a raised to the x is called an exponential function. So a is going to be a number in each problem, and we're always going to consider exponential functions that have a positive base and a non-1 base. The reason why we first consider a positive is so that we can plug in any type of value for x that we want, including like 1/2. So if we raised a to the 1/2, remember that's a square root, and we run into problems with even roots if we have negative bases, right? So if we're taking, say, the square root of a negative number. So to alleviate all those types of issues, we're going to always assume that the base of our exponentials are positive and that they're not equal to 1. Because if they're equal to 1, 1 raised to any power is still 1, so that's not an interesting function at all. Alright, so that's what we call the exponential function. So let's talk about how we graph exponential functions. Graphing exponential functions. What I'm going to suggest that we do in order to see the basic shape of an exponential function is just to look at a value table. That is a t-chart as a way of graphing. So we're going to pick different values for f, plug them in, find out what f of x is equal to, and then plot those points. So let's do something like, let's plug in 0 and see what we get. What's 2 to the 0 power? Well, that's equal to 1. So if you come over and look at this on a graph, let's see. So at 0, we have a function, a point on the curve at a height of 1. If I plug in 1, so I go over 1, that's going to be 2 to the first because I stick in 1 for x, and I get 2. So over 1, I have a height of 2. If I plug in 2, that's 2 to the second, which is 4. So over 2, I'm going to have a height of 4. And what you'll notice happens is that with a base of 2, each time I plug in one higher number, I'm going to double in size. So plugging in 3 gives me a height of 8. 4, 5, 6, 7, 8. Here is the curve. So as we go from left to right, you see it appears to do something like this, and continuing to grow in size. Now what happens if we go in the negative direction? What do I get if I plug in -1? 2 to the minus 1, you'll remember, means 1 over 2 to the first, or 1/2. So at -1, I have a point at a height of 1/2. If I plug in -2, that's 2 to the minus 2, or 1 over 2 squared, which is 1/4. So I go over -2, I have a height of 1/4, which is half as high as the previous one. If I do -3, 2 to the minus 3 is 1 over 2 cubed, or 2 to the third, so that's 1 over 8, so even half as high as the previous one there. So what happens is I go out to the left from there, it continues to get closer and closer and closer to the x-axis without ever touching it. So this is the shape of the graph for y is equal to 2 to the x. As a slight variation on the previous problem, let's look at graphing f of x is equal to 1/2 x. Instead of 2 to the x, it's 1/2 to the x. Again, I'm going to propose that we do this using a value table, picking values, say, like 0. Now 1/2 to the 0 power, as we know, is always going to be 1. Anything to the 0 power is 1. So let's plot these points as we come up with them over on our graph. Okay, so we go at 0, we have a height of 1. Okay, so there's our first point. If I plug in 1, that's going to be 1/2 to the first power. So if I go over 1, I have a height of 1/2 now. If I plug in 2, that's going to be 1/2 squared, which is 1/4. What you notice happening here is that this is like the reverse. It's a mirror image of what happened last time, right? 1/2 to the third is 1/8. So I go over 3, I'm right here. As I go out to the right now, the curve appears to be approaching the x-axis without ever crossing it, going that direction. Now what happens if I plug in a -1? Well, 1/2 to the -1 is the same thing as 2 over 1 to the first power, or 2. The negative exponent means to flip the fraction. So at -1, I'm at a height of 2. Now what do you suppose happens if I plug in -2? Well, you're going to get 1/2 to the -2, which is 2 over 1 to the second, or 4. So I go over 2, I'm at a height of 4. And if I go -3, I'm also going to get what you'd expect. You're going to get 8 using the same logic as before. 5, 6, 7, 8. So here I am. And so as I go this direction, that's the shape of the graph. Okay. Now by looking at these two graphs, we see a couple of characteristics show up. So let's talk about the characteristics of the function of this form. First thing I want you to notice is that the domain is all real numbers, meaning that all the numbers that you can plug into this thing include every real number that you can consider. So you're allowed to plug in anything. There are no numbers that are off limits. For example, when we looked at rational equations, we couldn't plug in things that made the denominator 0. When we looked at radical equations, we couldn't plug in things that made the underneath side of an even radical negative. Okay? But for these functions, we can plug anything we want to into them. However, the range, that is the set of all outputs, is always going to be the set of all values y, such that y is strictly positive. Okay, it's all positive real numbers. Those are the ones that we can get to. Right? If you scan up and look at these two functions, notice how they're all above the x-axis. This one is above the x-axis. Okay? Next thing I want you to notice is that all graphs of exponentials pass through the point 0, 1. This is true because f of 0, no matter what a is always going to be 1. The next thing is that if a is greater than 1, if your base is bigger than 1, like in our first example, 2 to the x, the graph increases from left to right, and the bigger the a, the steeper the increase. If a, still being positive, is less than 1, then the graph decreases. It goes downhill from left to right. And the smaller the a, the steeper the decrease. Okay? And in both cases, whether a is bigger than 1 or a is less than 1 but still positive, x-axis is always a horizontal asymptote, which is the mathematical way of saying that the curve approaches it but never crosses it. Now there's one other type of question I want you to be able to answer for graphing. So here, let's do this next example here. In this example, we're asked to graph f of x is equal to 3 to the x and g of x is equal to 3 to the x minus 1 on the same graph. So in order to do this, we're going to do, again, the value chart. I'm going to have a column for the x's that I choose. I'm going to create a column for my f of x's, which is what I get when I plug it into 3 to the x, and I'm going to have a column for the g of x, which happens to be what I get when I do 3 to the x minus 1. So if I pick, say, for example, 0. Plugging in 0 here, 3 to the 0 is 1. And if I plug in 0 here, that's going to be 3 to the minus 1, which is 1/3. Right? This is 3 to the 0. and this is 3 to the minus 1. Okay? So, looking at that on the graph, I'm going to plot these simultaneously. Actually, what I should probably do is let's get the whole set of points and then come back and graph them. Alright, if I plug in 1, I'm going to get 3 to the first, which is 3. If I plug in 1 in here, I get 3 to the 0, which is 1. If I plug in 2, I get 9, because 3 squared is 9. If I plug in 2 here, I get 3 to the first, which is 3. Let's go negative 1. If I plug in 3 to the negative 1, I get to 1/3. That's 3 to the minus 2, which is going to be 1/9. If I plug in minus 2, that's going to be 3 to the minus 2, which is 1/9. And this is going to be 3 to the minus 3, because minus 2 minus 1 is minus 3. 3 to the minus 3 is 1 over 27, really close to 0. So at a height of at x equals 0, my first curve is at a height of 1. Okay. At 1, I'm at a height of 3. And at 2, I'm at a height of 9. 3, 4, 5, 6, 7, 8, 9, which is right here. And then as I go to the left, I'm going to be at 1/3 and 1/27. And so here's the curve for f of x. Now, if I plug in 0, I'm at 1/3. If I plug in 1, I'm at 3. I'm at 1. If I plug in 2, right here, I'm at a height of 3. And so the graph looks like it's doing this. Okay? And then over here, it's 1/27 or 1/9, 1/27, so it's way down here beneath there. There's your G. So basically what it is it's this curve here for f shifted that direction 1 unit. That's what it looks like when you plot them on the same graph. There is a special number in mathematics that comes up very often in the context of exponentials. It's something called the natural base e. Now you'll remember in certain areas of mathematics there's another number that has special significance. In geometry as well as in a lot of different places in mathematics, we see the number pi show up. And as you're probably aware by now, pi is a very specific number. It's 3.1415926 and so on. It is a number that represents the ratio of any circle's circumference divided by its diameter. That's what you always get, is this number 3.1415926 and so forth. It's irrational, meaning that it has an infinite decimal expansion that does not repeat any pattern. And like I said, it shows up in a lot of different places in mathematics. There are several mathematical constants like that that show up in mathematical analysis. E is another very special number. We're going to denote E as the number 2.718281828459045 and so forth. Now, why we choose this specific number is a little bit beyond the scope of this class, although I will be able to give you at least one example of a place where this number shows up. But it's not as easy to explain as, say, pi, because pi has this geometric description. E is a little bit more mathematical in the sense that it's I'll just say it's harder to explain. We're going to refer to this as the natural base, and the function f of x is equal to this number e raised to the x is called the natural exponential function. Now, I will point out that your calculator knows this number. If you bought a scientific calculator, as was instructed as part of the syllabus of this course, that number is known to your calculator. It's important enough that it knows what that number is. You will have an e to the x button somewhere on your calculator. If you want to know what e is, you basically find e to the first power. Okay. On a standard calculator, you'll type in the number 1 and hit e to the x. On one of those graphing calculators or an algebraic expression editor, you'll type in e and then the 1 and hit equals, and you'll see again this number here show up. Now, in terms of its graph, obviously from the properties that we've already covered, we know kind of what it looks like, right? It's going to have that same shape as being an exponential curve. It's going to be increasing from left to right because e is bigger than 1. It is going to cross at a height of 1. Now, if we were to look at equals 2 to the x, f is equal to 2 to the x, we see a curve that looks like this. If we looked at 3 to the x, we would see a curve that goes through here and looks something like this. So where is e to the x? Well, e to the x is somewhere in between here. Okay, and also somewhere in between here. That's an estimate of what the graph looks like because it's between 2 and 3. Okay? All right, now let's look at a couple of applications where that number shows up. The first type of application would be one where they provide a formula for you. In this case, they provide one that involves that e that we were talking about before, that natural base. The function f of x is equal to 6.3 times e to the 0.0123x. This function describes the world population, f of x, in billions, x years after 2002, subject to a growth rate of 1.23%. Now, all that statement means right there, this 1.23% is where that number right there comes from. Now, use the function to predict the population in 2050. So basically all we're asked to do here, since we know x has to do with years after 2002, I'm going to find what 2005 minus 2002 is, which gives me, 2050 minus 2002, which gives me 48. So it's been 48 years since 2002. That's my x. So I'm going to find f of 48. So that's 6.3 e to the 0.0123 times 48 in the exponent. Now I'm using order of operations. I'm going to multiply in the exponent first, then I'm going to raise e to that power, then I'm going to multiply by 6.3. Okay? Now you may want to consult the user's manual for your calculator to get the order correct. If you have any questions, feel free to email your instructor about your calculator. So this becomes 6.3 e to the power 0.5904. If I raise e to that power, that gives me 1.8047. Multiply that times 6.3, and I have 11.4. And since the answer is in billions, we expect that 11.4 billion will be the world population according to this model equation in the year 2050. Another type of application I'd like to introduce to you here at the end of section 9.1 is the application of exponential functions to interest. Interest is that value that's calculated whether you're talking about savings and placing your money into a bank and it accumulates interest, or if you borrow money and you are asked to repay that money, that amount that you have to pay back accrues interest, and so you have to pay back additionally. So that's how you are paying to be able to borrow money. The particular type of interest I'd like to look at here is two types: compound interest at regular intervals and continuous compound interest. Now basically simple interest is that type of interest where if you have a certain amount that you place into a bank account, they're going to add a percentage of that original amount. That original amount is called the principal after so much time. So if you have an annual percentage rate of R and your initial amount that you started with is P, and you have it in there for so many years, your formula for simple interest is something like this: I is equal to principal times rate times time. Okay, where P is your principal, R is your interest rate, and T is the time that is in that account. But what simple interest rate does is always calculates how much is in the account based on the original amount. Compound interest works in the following way: that at regular time intervals they add a percentage of the money that's already in the account, not a percentage of the original amount. So that if after, say, 1 year they add 6%, when the next year rolls around, instead of adding 6% of your starting value, they add 6% of what's already in the account. That is called compound interest. Now they can do compounding periods more frequently than every year. If they did it annually, that would be once a year. If they did it semi-annually, they could do it twice a year. You might even have a quarterly or monthly compounding interest. Now, if you increase the frequency, you're going to get closer and closer to some upper limit, the maximum amount of money that you can make out of a compound interest account. That maximum amount you can make, no matter how often they do it, is called continuously compounding interest. So we've got two formulas here. One for n compoundings per year. A is equal to P times 1 plus R over N to the NT, where, and you have all the details in this paragraph, it's after T years, the final amount or the balance in an account with principal P and annual interest rate R in decimal form is given by, for n compoundings per year, this formula, and for continuous compounding, A is equal to P e to the RT, the other place where that number E shows up. So let's put these two formulas into practice. In the example you see here, we have $8,000 for 6 years. We want to invest, and we have a choice between two accounts. The first is 7% per year, okay, compounded monthly. The second is 6.85% but compounded continuously. Now, if they were the same interest rate, I would know automatically that continuously is better than compounded at regular intervals, because continuous is the best you can get. But because we've lowered the interest rate, it's hard to tell just by looking at the problem. We're actually going to have to do some calculation. Consider account 1. That's 7% compounded monthly. Okay, that means we're going to use the formula A is equal to P times 1 plus R over N to the NT. You're not required to memorize this formula. It will be provided on the test, but you do need to know how to use it and what the variables stand for. Alright, so the final amount is what we're looking for. The principal in both cases, account 1 and account 2, is going to be $8,000. 1 plus, now the interest rate for account 1 is 0.07. Recall that it does say to enter that in decimal form. 7% as a decimal is 0.07, divided by the number of compounding periods per year. It says it's compounded monthly. Monthly would mean 12 times per year. So for the n, I'm going to plug in 12. Raised to the 12 times how many years? In both cases, it's 6 years. Okay? So go to my calculator. I start inside the parentheses. 1 plus 0.07 divided by 12 is going to be 1.00583 repeated to the 72nd power. So I'm going to raise that to the 72nd power. Remember, we do exponents before multiplication. So that is 8,000 times 1.5201055. Multiply that times 8,000. I end up with $12,160.84. So now for account 2, we are asked to find the amount after 6 years for a 6.85% interest-bearing account that is compounded continuously. Now recall from above that the compound interest formula for continuous interest compounding is A equals P e to the RT. So A is equal to P e to the RT. Our principal is still 8,000. Our interest rate is 6.85%. Converted to decimal would be 0.0685. And then multiply that times T, which is the amount of time in years, 6 years. So now I would go to my calculator. I'd do this piece by piece. So I'd start by multiplying 0.0685 times 6 in my calculator. I do that, I get 0.411. And then I'd take this
e to the 0.411 and calculate that. If I've got a graphing calculator or the type of calculator that types everything out on the screen and then I hit equals to do all the calculations, I do e raised to the 0.411. Some older standard calculators, you might have to type 0.411 and then hit e to the x button after that. This one you'd have to equals whenever you're done. Either way, I get 1.508325, which I will then multiply times 8,000. 8,000 times 1.508325 is 12,066.60 cents. So that's what we get for account 2. Now the question is, what's the better investment? And clearly the first one up here is better because it ends up almost $100 ahead. So, I mean, that tells me in this case, that even though we're compounding monthly, which is not as good as continuous in general, we had a higher interest rate. And the higher interest rate was enough to make up that difference between the advantage that compound continuously would have bought us. Okay, so account 1 in this particular case is the better investment. All right, and that's the end of section 9.1 on exponential functions. We'll move on from there into 9.2.